And there we go. All right, so we've got to isolate this this exponential term. So we have to divide both sides by 5 first. We have to get that e to the 3t by itself. So we've got to divide both sides by 5. 12 divided by 5 will result in 2.4 e to the 3t. And now you natural log both sides. Bring the power out, the entire power, so we're going to bring that entire 3t outside of the logarithm. And now there is a slight thing we can do here that we couldn't do before. If you want to, you don't have to do this, but you can recognize that the natural log of e is 1. So you can kind of just drop it because anything multiplied by 1 is itself. But you can also keep it around. It's not incorrect to keep it around. But so then to finish, we have to solve for t. So we'd want to divide by the 3. So we'd have that t equals the natural log of 2.4 divided by 3. Or again, if you had left the natural log of e, this would also be correct. It means the same thing. We can just reduce if we scroll back up really quick. We do have one of these properties that the natural log of e is 1. So that's what I'm using to reduce that. That was a property that we had a little while back. So if you type that into a calculator, this is where you will get the 0.292 that I had accidentally had on the other one. I think some other people came in, so let me just reshare this really quick just in case. I'm not seeing any questions, so I assume I'll move on to the next one. All right, so in the next one, we want to solve for this t again, so we need to isolate the exponential term, just like always. So, but here we don't have multiplication, we have that we are subtracting that 5. So to kind of get that over to the other side, we have to add 5 to both sides, giving us e to the t minus 1 equals 10. Once you've isolated the exponential, that's when we take the natural log of both sides. You want to bring the entire power out, and since we have subtraction in that power, you should put it in parentheses. So whenever you have addition or subtraction coming from the power, put it in parentheses. The reason for that is if this was, well, depending on how you'd want to then finish solving this question, you could say you can divide both sides by the natural log of e. You could, well, okay. For this particular question, you could say the natural log of e is 1, and therefore you can kind of drop it. But if that was anything besides the natural log of e, if that was the natural log of 2, the natural log of 5, you know, whatever, it'd have to stick around. So then depending on how you'd want to finish solving the problem, you would either have to divide by that natural log first before dealing with that -1, or you'd have to distribute it through. So if you don't bring that power down in parentheses, you might end up doing it. You might end up doing the rest of the problem incorrectly, which isn't good. So I'm personally going to say the natural log of e is 1, so I'm kind of going to drop that piece. Again, if you keep it around, it's not incorrect. You can do that, it's perfectly fine. So I'd have t minus 1 equals the natural log of 10. So then add 1 to both sides to solve. So this will result in approximately 3.3. Questions, concerns on solving using logarithms? Okay. All right. Well, then the last little bit we have to talk about in 1.6 is this last piece here. So so far we've been writing all, my English is starting to break. At this point in time, we've been writing all of our exponential equations as this p naught a to the t. But there's actually another form we can use as well. It is used in slightly different context, but you can also find equivalent forms. So there's this other form that we're going to start using, which is an e to the kt. And that's presented right up here. I just wanted to write them off to the side because I want to show something with them in a second. And we kind of have these two relationships where k is equal to natural log of a, or e to the k equals a. And I'll kind of point out why that makes sense in a second. So k is going to be called the continuous growth or decay rate. So when we start 1.7 in just a second, we're going to be doing some questions where it says, you know, something is growing at a continuous rate of, or decaying at a continuous rate of. If you see the word continuous, it means you're using this e to the kt form. If you just see the word rate and there's no continuous, then we're using the a to the t form that we already had. So let me kind of, this one, if you just see the word rate, we're using this. If you see the word continuous, which is usually used with rate, so don't get confused there, but it's continuous rate versus just rate. And kind of the wording of the problem is going to then tell us which form we're going to use. But we can also always find an equivalent, you know, the equivalent other form given an original equation, which is what we're going to do down here. We're going to convert between the two forms. But before we get to that, so way back when we started talking about exponential functions, we had these two specifications. It's either exponential growth or exponential decay. And these two pieces we already wrote down, but to remind us, if the a value is greater than 1, we had exponential growth. And if your a value turns out to be between 0 and 1, it was exponential decay. And we're going to have the same exact specifications for this k value as well. And we kind of have the link between the a and the k value. So if a is greater than 1, k is going to turn out to be positive. And in that situation, when k is positive, we have exponential growth. So it's essentially just giving us the new way to, if we have this new form, how do we tell if it's exponential growth or decay? Well, it depends on the k value. And is the k value positive? Or in the other case, if a was between 0 and 1, k turns out to be negative. So if k is negative, we have exponential decay. Decay. Let me rewrite that a. That looks really... K kind of behaves, maybe I shouldn't say behaves, is somewhat like R. So in the A form, we had 1 plus R, where R was the rate. Essentially, the K value here is the rate. It's just the continuous one. So they kind of are similar. It's just for the different forms. Hopefully that makes sense. So we have one form that has an R and one form that has a K. Now, again, once you're given one of the forms, you can always find its equivalent other form. How the heck are we going to do that? Well, if you look back over to the side where I wrote both of these forms, what's the only thing that differs between those two forms? The p's match up, the p naughts match up. They both have an exponent of t, but the only thing that's different is the a versus the e to the k, which is why we were given these relationships here. I personally just use this relationship because I think it's easier to remember, because it kind of, you just look at the two and say what is different if I want to say that these two equations are the same thing, if I want to say that they're representing the same set of data, then I want everything to be equal to each other, so A must have been equal to e to the k. So hopefully that makes sense. So that's essentially what we're going to use to be able to find the equivalent, other form for these exponential functions. Let's scroll down just a little bit. Try to keep some of that in there. Nope, too far. So if we look at this first one and we want to convert to the other exponential form. So say we want to convert to the other form and we're given p equals 1000 e to the 0.5t. Sorry, my cat needed to come in. So again, the only thing that differs between the two types is the a versus the e to the k. So this p naught that we already have is going to stay the same p naught. The p naught doesn't change between the two forms. But then we have that we must have that e to the k equals the a value we want. Well, we have the e to the k, it's e to the 0.05. Now remember, e is a number, so this is something that we can plug into our calculator already. If you're not aware of where the e button is, there's kind of two choices. You can either, if you have a TI-84 or 83, you hit second, and you can either hit the division symbol, because if you look at the division, there's a little e above it, and that will just get you e in general, or you can hit second and then the ln button. This will get you an e to the x form, so it will kind of immediately put you up into an exponent. I usually just use the division one, but whatever floats your boat. So if you punch in e to the 0.05 into your calculator, you're going to get that a is approximately equal to 1.051. That's a really gross approximation sign. And essentially now we have both of the two pieces we need to write a p naught a to the t form. So we just write it. So we have p naught was 1000, a we just found to the t. So essentially these two equations are going to give us the same set of data. So we can always jump between the two forms if for some reason we need to. I'll be quite honest, it's not often that you need to, but if you ever need to, you can. Questions on that before I go through the rest of them? Okay. What about if I start with the opposite one? So I start with an a to the t and I want an e to the kt. Once again, p naught doesn't change, so p naught's still going to be 500 in the other form as well. But if I look at e to the k equals a, well, now I have a. So I have that e to the k is going to be equal to 1.06. Well, I need to solve for k, so I can solve for k by taking the natural log of both sides. And if I can do two steps at once, sorry, my Cortana pulled up, go away. There we go. So if we take the natural log of both sides, now I'm going to erase something and put it on the same line because I've run out of space. So once you take the natural log of both sides, then you'll bring the k out front. If we treat the natural log of e as 1, because it is, then we just have that k is going to be equal to the natural log of 1.06, which is one of the other relationships we were given. But again, I just usually use the e to the k equals a, and then I just solve for it manually because e to the k equaling a makes more sense to me because it kind of falls out from just looking at the two equations next to each other. So if you ask your calculator what natural log of 1.06 is, you're going to find that k is approximately 0.058. Screen is frozen. hopefully resharing it fixed it. Looking good now? Can you see my little scribble? Yep, okay, cool. All right, what do we, K equals 0.058. So then we have the two things that we need to write the equation for the e to the kt form now. So we have P equals P naught was 500, sorry, e to the k t. Okay. And then let's just do two more of each example just to kind of, you know, hit it home. So say I go back to, so number 3, now we have an e to the kt form again. So once again, P naught does not change. So P naught is still 25. And then if I treat e to the k is equal to a, but here our k is 1.2. So e to the 1.2 is going to be equal to the a value we need. Punch that sucker into a calculator, you're going to get that a is approximately 3.32. Once you have a and P naught, you've got all you need. So P naught was 25. What am I writing? A was just found to be 3.32 and to the t. Okay. And for the last one, once again, P naught does not change between the two forms. Since I always use the e to the k equals a format, I would get here and then have to take the natural log of both sides. I'm going to do 2 steps at once and bring the k out. Whoa, I didn't take the natural log of that side. So I took the natural log of the left and pulled the k out at the same time. Natural log of e is 1. Just to save myself a line, I'm just going to cross it out. So if we punched into our calculator natural log of 0.92, we get that our k value is going to be negative 0.083. And yes, it should be negative. And that makes sense because we are told if a is between 0 and 1 and a is less than 1 here, then k should be negative. So that does make sense. So then we have P equals our P naught e to the k we just found. T. So we have this new form of e to the kt instead of a to the t. It's going to be used when we have word problems. It's going to come up when we see the word continuous. And if we don't see the, well, if we see the word rate and it doesn't say continuous rate, then it's a to the t. If it says continuous rate, it's e to the kt, and we'll see something in just a second where technically we get to choose. And I'll say why we get to choose when we get there in a second. Questions, concerns about 1.6? Because we'll jump to 1.7 then. Now 1.7 is just more of these exponential and logarithmic stuff. It's kind of using 1.5 and 1.6. There's not a lot of new, there's a few new definitions, but all of the stuff we technically already have the tools to do. Can't see the screen. Well, I'm about to change to 1.7, but let's just make sure we can see it in general first. Can you see now? Okay. All right, so we've got this new form, e to the kt, that we're going to start using in 1.7. So I do have to jump away from this now, but of course you can always find it later. So I got to, I don't think I've pulled 1.7 up in my little note-taking thing yet, so let me do that, and then we'll share 1.7. Come on. All right. So 1.7 is called exponential growth and decay. And again, it's just doing more exponential and logarithmic stuff. We've got most of the actual techniques. We just have maybe 1 or 2 new definitions to look at. But let's look at this first example first. There's a spill of radioactive iodine. The radiation level was 2.4 millirems per hour, so an evacuation was ordered. The level of radiation decays at a continuous hourly rate of K equals negative 0.004. So since that word is continuous, since we have continuous in the question, we know we're going to use the e to the kt form. And they were nice and they named it K, but even if they name it K, you need to triple check that you have the word continuous, because they could try to be tricky and just say hourly rate without continuous and just call it K for giggles. Anyway, but since it has that word continuous, we know we're using the e to the kt form, and since it's decays, this negative makes sense. Even if they didn't give us a negative there, since it says decay, we would have had to make it negative. So always remember that if you see the word decay and the thing you're given isn't already listed as negative, you got to make it negative. They might say decays at a rate of, what would this be, 0.4%. Maybe they don't tack the negative on the percent. Anyway, what is the level of radiation 24 hours later? So we essentially need the equation and we just need to plug in 24. So I need to figure out what my equation looks like first. Well, we're given K, so that's nice. And P naught, well, again, P naught is the initial condition, so the initial value we're starting with. And we're told that we start with 2.4 millirems per hour. So that's going to be our P naught. So we can find our equation to be 2.4 e to the negative 0.004 t. And then since we're asked for the radiation level, 24 hours later, we know we just want to plug in 24 for that time, because time is in hours here. So 2.4 e to the negative 0.004 24. Good now, Sam. Cool. So we plug in 24 to that equation we just found. Plug that sucker into a calculator. You should get about 2.18, and this is a P value, so it's going to be the same units as the P naught. The P naught was in millirems per hour, so this will also be in millirems per hour. So whatever the units of the P naught is going to be the units of the result as well, in case I hadn't made that clear yet. Okay, I'll pause for just a second. Then we're asked to find the number of hours before it reaches the maximum acceptable level. So now we want an amount in hours, so it looks like we're going to be solving for a t. So we want to make sure that the final level is 0.6. So we're essentially being asked to solve for t when we let the resulting value be 0.6. So negative 0.004 t. And this becomes a situation where we have to solve using logarithms. Again, this section we have all the tools, now we're doing lots of word problems instead of just, here's an equation, solve it. So as always with solving with logarithms, we want to isolate the exponential term first, so we've got to isolate this guy. So we've got to divide both sides by 2.4. Maybe I should extend that all the way over so it divide by 2.4, which will result in 0.25. On teams, not exactly, because for some reason there's been like a glitch lately where it's not saving correctly to teams. But if you go to Blackboard, I'll show you super quick because I have Blackboard open already. If you go to Blackboard, because someone also was looking in the wrong spot for them, so maybe other people are looking in the wrong spot. If you go to course content, all the lecture recordings are in the lecture recording folder under course content. You can access them on Teams for like a little while, but then again, it's bugged for some reason. So they're all on Blackboard. All right, where were we? So we got there. So we've isolated the exponential. So now we're at the step where we have to take the natural log of both sides. We bring the power out. And just to show that it's still the same thing, I've been doing that, the natural log of e is 1, but let's just say, again, we don't want to, maybe you don't want to do that. Maybe you feel better by just dividing by everything, and that's perfectly fine as well, whatever floats your boat. If you want to let the natural log of e be 1 and then just divide by the negative 0.004, so this would be the exact same thing as doing this. I just want to write them both just in case someone prefers keeping the natural log of e around. But the point is that we wanted to solve for this t, so we needed to divide by everything that was also on that side. And then I wrote t on the other side, so hopefully that didn't confuse anyone. Let me know if it did, and I can rewrite it. This will result in approximately 346.57 hours. So after approximately 350 hours, it will get down to that acceptable level of 0.6 millirems per hour. Questions, concerns? Okay. All right. I'll try to leave that one in, that last part. So the population in Kenya was 18.9 million in 1984 and 46.1 million in 2015. Assuming exponential growth, find an equation for the population of Kenya as a function of time t in years since 1984. Notice in this question, there is no rate, there is no continuous rate. So since it does not have, let me see. I'm gonna circle this part because this is kind of where it would have shown up. Since we don't have rate or continuous rate, we get to choose. So you need to be careful. If it says rate or continuous rate, then it's kind of locked into what form you have to use. Since we don't have either of those two words or phrases here, since it doesn't say rate and it doesn't say continuous rate, we get to choose which one we want to work with. Now, this is one of the type of questions where it's finding the equation. We've done one of those for an a to the t form in 1.5. So because we haven't done one yet for the e to the kt form, that's the one I'm going to choose to use here. So we're going to choose to use the e to the kt form because I'm choosing to use that one. So we have that long process from 1.5 that we used with the a to the t form. That will also work with this one. But we can shortcut this one a little bit because we know what P naught is. So I'm going to go ahead and use that little shortcut of knowing what P naught is. Well, maybe no, I'll show you the other way anyway, just in case. So usually what we'd have to do in the long way is we'd have to write the 2 points that were given in this equation first, and then we would divide them. That was kind of our first step. So here we're using T as in years since 1984. So that first point that I have is going to be 18 point, well, nope, I want to put that one on the bottom. 18.9 million people. Let's say I don't know what P naught is. I don't know what K is, but I know that T here is 0 since 1984, is 0 years since 1984. And then the other point would give us 46.1. Don't know what P naught is. Don't know what K is. 2015 is 31 years since 1984. So just like with the A to the T form, we write them both in that equation form, and then we divide the two equations. So this is a process that we wrote down in 1.5, but it works with this form as well. So if I divide 46.1 by 18.9, I'm going to get 2.439 approximately. The P naughts cancel each other out. And then we have that same situation where we now have to subtract exponents. So we have e to the 31k minus e to the 0. So we're left with e to the 31k. So this comes from 31k minus essentially 0k. That looks like okay, but so maybe I'll just write 0. What we'd have to do here to finish solving for k is now we essentially have something, so let me just rewrite it. We have something where we'd have to solve for k, so we have to take the natural log of both sides. And if I can, I'm going to do 2 steps at once and take the natural log of that side and bring the exponent out at the same time. So this used to be that. Natural log of e is 1. Divide both sides by the 31 to solve for our k value. Honestly, the shortcut way wouldn't have saved us that much work. We still would have had to do the bulk of what we just wrote down. So might as well have seen the full out in case you can't take the shortcut. 2.439. 42439. Gotta type it in right. Divided by 31 is about 0.02, let's say 88. Let's take 4 decimal places. The only other thing we need is P naught. In the full version, so I'm going to take a little bit of shortcut here. In the full version, what you would want to solve is you would plug, whoops, what am I writing? 46.1. You would plug that K in to one of the two equations you had and solve for P naught. You would just have to type in that e to the blah thing and divide the 46.1 by it. But we know P naught here, so let's just use the P naught that we're given. Because remember, P naught is the starting value, and we know that we started with 18.9 million, so we know that P naught is 18.9, so let's just use it. Once we have P naught and K, we can write our equation. P naught is 18.9, e to the 0.0288 t. So this is a similar process to what we did with the A to the T form. We did like an example with wolves in Wyoming, I believe, from 1.5. This is the process just with this other form. One thing I want to mention quickly, I'm going to scroll down a little bit so I have a little bit of space to put it somewhere. In the homework, you have ones that look like this, and I don't know, it gives you like a point. And it tells you what this value is. Let's say 25. and it asks you to find the exponential equation for this, you're going to use, well, this process, but for a to the t. So you use the a to the t form, but this is the process that you want to use. You have 2 points, and you want to write the equation of the line, which is exactly what, not the equation of the line, the equation of the exponential function. They're not that bad. They just take a little time. I know they're long and tedious, but they're not that bad. Questions, concerns before we move on? We're getting to the end of, we've just got a tiny bit more of 1-7, so we'll hopefully have a little bit of time to talk about the homework if people want to. All right. So this definition, can I say what again? The thing about the homework? You've got ones that look like this that give you some kind of, you know, it looks like this, and then it asks you to find the equation of the exponential function. So you want this, and you have 2 points. You have 0, 25, and 15, 6. So you're going to use the process that we essentially just used here, but for the a to the t form, which we did in 1.5. So it's essentially the thing we just did, but with the a to the t form, which was written down in the notes in 1.5. So if you go back to the wolf example in 1.5, follow that process, which is the exact same process we just did here, but the different format might be confusing. But you have 2 points. It gives you 2 points from the graph. Now you just take those 2 points, kind of forget the graph exists, and go about finding the equation with the process presented in 1.5. So this is kind of the new stuff for 1.7. The only kind of new definition we need. So the doubling time of an exponentially increasing quantity is the time required for the quantity to double. And the half-life of an exponentially decaying quantity is the time required for the quantity to be reduced by a factor of 1/2, essentially be 1/2 the amount of what it started with. So let's say we have this example of the release of chlorofluorocarbons used in air conditioners and household sprays destroys the upper atmosphere. The quantity of ozone is decaying exponentially at a continuous rate of 0.25% per hour. What is the half-life, of ozone? Since we're working with continuous, we know we're in the e to the kt form. So I want to figure out what my k is. Well, that's going to come from the 0.25%. So I've got to change that over to a decimal first. So I have 0.0025, but I'm also missing something on that still. And that's because of the fact that we're told it's decaying. Again, when you see the word decay, it might not necessarily list it as negative, but it needs to be negative. So this rate does need to be negative because we're decaying exponentially. Now, some of you might ask me, well, what the heck is P naught? I need P naught to be able to figure out the rest of this question. No, you don't. So for half-life and doubling time questions, you don't need P naught. If it really bugs you to not have a number, pick one. Whatever number you like, pick it. Make it P naught. But here's the reason why we don't need it. So I have some P naught e to the negative 0.0025t. And I want to know, maybe now that arrow looks like it's, well, yeah, let me just get rid of the arrow. So I want to know the time it takes for this to be cut in half, the amount that I started with to be cut in half. So I want to solve for t, so I need to know what value to plug in for p over here. Well, if I want it to be cut in half, the amount that I started with, I'm just going to say let it be half of what I started with. I don't need to know what that value is, and you'll see why in a second. But we don't need to know that value. I can just say, let it be equal to half of whatever I started with. Because the point is, the first thing you're going to want to do when you're solving for t here is you want to isolate that exponential term. So we're going to divide both sides by p naught. Well, then they just all go away, and we're just left with 1/2 e to the negative 0.0025t. So it didn't matter what value we started with. I could let it be whatever number made me happier, if that floats your boat, or I can just let it be a generic p naught because it's going to go away in the first step of solving anyway. But then to finish solving, once again, we're at a step where we need to find something that's in an exponent, so we're at the spot where we take the natural log of both sides. And if I can, once again, kind of do two steps at once we take the natural log, we're going to pull out the exponent. If that's freaking anybody out, let me know and I can do the two steps, but I'm just being lazy. Natural log of e is 1. So to finish solving for t, we would just have to divide both sides by the negative 0.0025. So t is going to be approximately 277.259 years. Usually I get the question of where the heck did the negative go? And the negative, quote unquote, disappeared because the natural log of 1/2 is a negative number. Why did you put p naught on the left side? Right. So the point here is we're asked for the half-life of ozone. Well, my definition up here tells me that the half-life is the time required for the quantity to be reduced by a factor of 1/2. I essentially want to end with half of what I started with. Now, I don't know how much I started with, so I can't make that a number. If I knew that I started at 100, then I would say that I want to end at 50. But I don't know what I started with. I just know that I started at p naught. So I know I want to be half of p naught. So that's why it also ends up on the left, because what I want to end up with is half of what I started with. And p naught is what I started with. So half of what I started with is 1/2 p naught. Does that make sense? Okay. Now the only difference with, you don't need the value for p naught. That's correct. We do use p naught because we need to write it in the equation, but we don't need to know what it equals, which I think is what you're getting at. And again, if you prefer, you can pick absolutely any number you want. You can plug it in if it makes you happier, but we don't need the value. With a doubling time question, so say we were asked for the doubling time instead of half-life, all you would do is use 2, well, maybe p naught. I know I'm using q's here for some strange reason, but you would just set it equal to 2 p naught instead of 1/2 p naught. So here we set it equal to 1/2 p naught, and it's starting to lag a little bit. If it's a doubling time question, you'd want to set it equal to 2 times p naught because you want the initial quantity to double. Hooray. Questions, concerns? Okay. Let's super quickly breeze through this last bit then. I'm trying to save a little time for questions, but the last thing, again, we kind of already know how to do these. We just need the context of it. If we're talking about interest, so say you put an amount p naught into your bank account that's going to pay you an interest of r per year. P is going to be the balance the balance after t years. We have kind of two situations that we're going to go through. In other classes, you might realize that there are other ways to compound interest. But in our class, we're only going to talk about interest that's compounded annually versus continuously. So here's the equation you're going to use if its interest is compounded annually. The initial value you put in, 1 plus r to the t, which looks suspiciously like this, because it essentially is. And if the interest is compounded continuously, now the only thing here is when it's presented as interest, it's usually written as RT instead of KT. But it's essentially what we have here is we're just now adding the context of interest. It's still using, if you don't see the word continuously, you use the A to the T. And if you see continuously, it's the E to the K T form. So it's kind of the same idea. It's just that now it's put in terms of interest. I'm going to set up these last few examples, and I'll write the answers on Blackboard for anyone who wants to see them to look at later. But there's stuff that we've already done a bunch of times. It's just now in terms of the context of interest. And then I'll super quick take questions on homework if people have them. So say you have a bank advertising an interest rate of 2% per year. So that means that R is going to be 0.02. If we deposit 10,000, so that's our P naught, how much will you have in 3 years? If it's annually, well, we're looking at P naught A to the T. So we have 10,000, 1.02, 1 plus R to the T, which in this case, we are then asked to plug in 3, 4. And that's where I'm going to leave that piece. Versus continuously, we're using the E to the RT form. So 10,000 E, I don't know why I put a parenthesis there, 0.02 T, plug in 3. So y'all can punch that into your calculator. And then the setup for the last one, and I'm not going to go through it exactly. You deposit 10,000, have an interest rate of 1.5% per year continuously. Of course, now my thing stops working. How long until you reach 12,000? Well, that's asking you, your equation you're working with is 10,000 e to the 0.015 t, and you want to set that equal to 12,000. So this would be a problem where you'd have to use the natural log to solve for it. So that's a setup for all of those. And I know we've only got 1 minute left, but questions, concerns on any of that? Questions, concerns on the homework? I've got a couple minutes before my next class, so we can go a little longer if anyone could stay. Otherwise, if you're good, then bye. Exam review is going to be popping up on Blackboard probably later tonight, by the way, because your exam's on Wednesday. This week, it's 1.5 through 1.7. So we've now covered everything on the homework. Hooray! SI has exam review next Tuesday. I am slightly still figuring that out, Benji. I am saying that anyone who is physically able to come to campus needs to come to campus. If anyone is quarantining or isolating, that's different. But anyone who is physically able to come to campus needs to be on campus. Will the exam questions be like the quizzes or the homework or both? So think about it this way. The exams are written by me and so are the quizzes. So the exams are somewhat more like the quizzes and like the warm-ups, and also take a look at the review that I post because I write that as well, as opposed to your homework, which is written by Wiley. I'm not saying that Wiley isn't a good thing to look at if you have the time, but it's better. Your time is better used looking at your quizzes, thinking about the warm-ups, and looking at the review that I post, because those things are all written by me, so that's kind of how the exam's going to look as well. Okay. I should have pulled this up already. Let me get that up really quick to look at what that one looks like. Let me stop the recording. Let me do that too. Stop.